At the end of class last time, we went through a series of slides that I recommend that you, this one paragraph, we analyzed it in infinite detail with that series of slides. Do you remember that? And because it explains exactly what happens with the cut, and Bratko has a really good description here. And if you parse exactly what he says through the slides, I think you'll see precisely what the cut does. Basically, you can think of the analogy is when you go over that in a parking lot, whenever you can enter the parking lot but you can't exit through, or maybe it's the other way around. You can exit the parking lot by going over those spikes, but then you can't get into the parking lot the other way. So you can think of that cut as being that way. Cut always succeeds, but you can't backtrack over it. You'll fail. And of course, once you fail, there is no backtracking, right? I mean, once that fails, that fails. I mean, well, anyway. So we went over that. It was kind of quick, but the slides are up there available for you to study. So what we want to do now is we want to continue on. So here's our demo. Now, what's the difference between a green cut and a red cut? Do you remember that? So here it has green cuts, could be removed. What does that mean? Anybody? What is a green cut? What does it mean, could be removed, huh?
Yeah, just for efficiency.
Yeah, it's just for efficiency. If you take the cut out, it still works correctly, and that's just for efficiency, okay? There is no such thing in, Prolog doesn't know the difference between a green cut and a red cut. All it knows is that it's a cut. But we know that if we put it in there in such a way that it, such that if you take it out, such that if you take it out, if when you take the cut out, the results don't work, then it's a red cut. Okay. So, and here we saw an example of, we saw two examples of a red cut. Here's this example of a red cut was the second version of F, which, wait, no, I'm sorry, that was a green cut. This third version, this was, if you take these cuts out, then it won't work correctly. All right, so now, Gesundheit. So now let's take a look at how we can use cuts. All right, first example that we're going to look at now is max. So check out up here. It says max x, big X, big Y, big M, max. Max is the maximum of X and Y. So here, let's do a little demo of this. So what do you think, guys, if I say max 3, 4, and then capital M? Now here again, what we're doing is we're assuming that the last argument is sort of like where we get our result. So what is max 3, 4? What's the maximum of 3 and 4? 4, yeah, so M is 4. And just to show you that it wasn't just a fluke, taking the second one each time, let's do max 4, 3, and M, and obviously it's still 4. Oh, is there another solution? No. Now, did you see that? Okay, so, all right. So, tell me, here's our first version of max. So what is just without cuts? What's the way to do this? When M is obviously going to be either what or what? Here, max is, it's either going to be X or Y. So what should the rule look like? Then this variable will be, yeah, if X is greater than Y, say it again, if X is greater than Y, then this variable will be this variable. Yeah. Okay. So max X, Y, X. Are you with me? Just notice how this first one is this last one. Yeah? If what? X greater than Y. Okay? And then what about the other one? Max, wait, YY? Max YY? There's 3.
Max XY.
Oh, sorry.
Max, yeah, X, yeah, max X, Y, Y, if what? If what?
Y is greater than or equal to X.
Yeah, well, x is less than. We'll just have them be one and be equals and the other one not, right? Is everybody good? Okay, so now let's see how this works. Let's test this one out. Let's do, oh, I just did max. That was that max, right? Okay, now how about this? Oh, so how about a more efficient version now with cuts? So in other words, why do this test and do this test? Once we know this test, what do we know? If it does what? If it passes this test, what do we know?
We don't test the other.
Yeah, okay, so how can we do a second version more efficient? Second version, so what's the logic? If x is greater than or equal to y, then what? We match, yeah, max matches with x. Otherwise, so we don't do the test, we say otherwise. So how do we do this with cuts? These are going to be red cuts now. So come on, I'm waiting. Okay, so max x, y, x if, or max 2, there's our second version. So max 2 x, y, if what? X greater than or equal to y, then what? Cut. Right? So now, if that succeeds, what's going to happen? Does the cut always succeed? Suppose x is greater than or equal to y. Then we'll go to the cut, right? Does the cut succeed when we execute it?
Yes.
It always succeeds. When does it fail? On backtracking. Okay, so now what's the next? So now what's the next otherwise max match y?
X2, X, Y, Y.
Not, well, x, y, y, but then if we did x, y, y, x would be what kind of a variable?
Oh, blank.
It would be a singleton, right? So we want blank. Okay, next. Is everybody with me on this, on how that works? Okay. So, now check this out. Let's predict max 311 and max 2 311. So here let's do max 311. Now, what should this be? I mean, should be no, right? And what about max 2 311? What should this be? What happened? What happened? Yeah, you got to be careful here, huh? Why did that happen? Can somebody explain that? Here's max, huh?
Does it pass the cut, so it went to the next one?
Wait, did it pass the cut? Wait. So this is 3, it did 3, 1, right? Wait, it did 3, 1, 1. So it come here and it came here, and this was what? 3, 1, huh?
They're both greater than or equal to 1. 3 and 1 are both greater than 1.
Oh, but wait a minute. I thought we tested max 2 with a variable for,
Well, it won't get to the cut. Because X.
But doesn't it always go
Because there's two different values for X. If you gave it the first definition.
okay, yeah. So that's the correct, that's a good observation. When we do max 2, 3, so if this is 3 and this is 1 here, when we go here, this is 3 and this is 1, so this fails right off the bat. We never get into here, right? Look, if this is 3, see, watch the cursor. This is 3, this is 1. Okay? So that means that when we come up here, if this is 3 and this is 1, this won't even get into the if. So it will come here. Now what happens? This, yeah, this is 1 and this is 1 and it succeeds. So we never got through, yeah, you're right, we never did execute the cut. Oh, interesting. Okay, how are we going to solve that? Third version, corrects the query, max 2, 311. So now how are we going to fix that? You see how to fix it? See how things are not what they seem. Things are not always what they seem unless you think about it really hard in Prolog. So what happens? How can we correct this? So here's our third version. Corrects this query. Max 3, xy max, if what?
Keep it all in one rule instead.
Ah, interesting. So x is greater than or equal to y. Oh, by the way, we're not doing x, y, x, and we're not doing x, y, x, and y, x, x, right? We're going to do, I'll have them all be variables. So x, y, max. So if what? Is greater than y, then we do what? We cut, and we do max match x. All right? Or what? Right, because if x is greater than y fails, then it'll go to the other one. So max match y. Okay? Does everybody see how that works? So you got to be careful. Yeah, question?
How can we tell where the order of operations is?
The order. Oh, it's always left to right. The goals always search from left to right. Are you talking about the difference between this one or this one? The semicolon?
Yeah. When max match x fails, how far does it go back with the or?
This, no, well, because we did this, it doesn't. Because of the cut, it doesn't. Are you with me here?
I'm not sure.
Okay, yeah, think about that. Yeah, this, you know, it's deceiving. You really have to think. I mean, these things, they look simple, but they're deceiving. You really have to think it through. Okay, so now let's check out my member. Okay, so here's my member, and its element x is a member of list L, and it's non-deterministic, and it has several solutions. So I think what we'll do is we're gonna scroll to the definition of my member, and so this says x is a member of the list that has the car. You know that the car is x. That's the base case, and then what is the recursive case? Didn't we do my member before? Do we not know how to do this?
My number x, comma, space.
Yeah, x comma anything L if,
Remember X, L.
yeah, if my member XL. So that's our old version of my member. So let's just check out how my member works. If we do my member, whoops, no, it's underscore. I get Lisp and my underscore, my member, let's do A, and then we'll do, whoops, A, and then we'll do the list A, B, B, C, and then we'll do, you know, like A, B, C, okay? So we'll do this. And now if we do this, what happens is it's true, and if I search for another, if I see if it's true again, it will be true again because there's two A's in there. Are you with me? So now what we want, we want a non-deterministic version of my member so that once it succeeds, that's it. So now, how can we do that? So here's the second version, find only the first occurrence, okay? Oh, scrolled kind of quickly there. So my member 2 Now, that's the same as before, right? But with the cut. And now what? I think the second one is the same, isn't it? If my member XL. But this has the cut. So now that it has that cut here, what we're saying is that if we do this my member 2, right? Now what's going to happen is, when we press return, it gets that and boom, there's no more solutions. So it knew that there were not to search anymore because of the cut.
What I don't understand is that when you have the cut, that's like saying if you go through the cut, you can't.
If you go through the
Go
cut,
back.
you're right.
But
You can't go back. Yeah, that's a good.
How is that helping on this one? Because let's say you go through to my member to the second part, and you can't go back.
No, that means, because what happens is, when it succeeded the first time here, then to search for another one, it would have to backtrack through this cut. But that's it. When it tries to backtrack through the cut to get the next one, it can't. It fails. Are you with me on that? See, look, it's kind of like this. Let's go back to this slide. Look, here it's, on this slide it says, if Q fails, the query can succeed through V. All right? So down here, if you see, let me see, I might have. Well, anyway, let's just read this. You see where Q is there on the slide? If Q fails, then you can backtrack up to C and you can get to V. But if T fails, once you go through that cut, if T fails and you try to backtrack, you can't. It'll fail right there. So that prevents V from even being tried. And you see what I mean? And where is V over here on the right, in the rule? Where is V? That's the one after. You know, there's a C if PQ cut STU, and then that C if V. V will never happen if, see? This is a more general setup, but it's the same thing of what we just looked at. Are you with me?
That makes sense, but the my member doesn't.
Oh, well, but isn't this the same shape as the my member? Yeah, because there's a cut, there's a rule with a cut, and then there's a rule with the same head, but that doesn't get executed if you go through the cut.
Won't you always go through the cut because the cut is not?
No, not if you fail in PQR.
But on my member there is no PPR, it's just cut.
Well, I know, but the success, oh, I see what your question is. But you see the success or failure is in the success is in this matching here. This has to match before you can do this. If this doesn't match, you will go to here, and this cut will never happen. Are you with me? See, yeah, see it. Oh, that's a good question. Do you see that the arguments have to unify in the head of the rule in order to even get into the rule? Oh, yeah, maybe that's what was, and that's a big paradigm shift. You are right. You have illustrated another aspect of the paradigm shift. Do you see the arguments of the head of the goal have to succeed? Right, and that's how the cut can never execute. You were thinking that because it's the base case, yeah. Ooh, that was a good observation. Is everybody clear on how this works? That was a good discussion, a good question. All right, are we good? Okay, let's take a look at add now. So here's the definition of add. Here's the specification of add. Add XL1. If X is a member of L, then L1 matches with L. Otherwise, L1 is equal to L with X inserted. Now, this is kind of tricky. Let's do a couple of adds. Let me do a couple of adds and see if we can understand this. So let's do add, and we'll do A, and then we'll do list B, C, D. Oh, by the way, add has what arity? 3. and then L. So now, tell me, so what does it say about add? Can you predict what this is going to be? If X is a member of L, is X a member of L? No. So L1 won't match L. What will it be? With what? Inserted. So you see that that's what it is. Boom, and that's the only, and it gets inserted at the beginning. Are you with me? But look, if we do add, only here, if we say, oh shoot, if we say BAD, now what's, now is X a member of L?
Yes.
So what is L? So what will L be? Oh, it's too bad we have L in the middle on the definition, but L1. Yeah, exactly. Could have chosen my letters better on that. All right, does everybody see that? So now, what do you think? How do you think? What do you think we should do to? How do you think we should write add? Implementation of add. It's 3. Has 3. So add. No. Here's the big hint. Add XLL if what? And we can use, obviously, what are we going to use? Let's use the built-in member.
Member XL.
Mm-hmm. But then the cut. Okay? Actually, maybe, well, okay, we'll go ahead. And then what's the next one? Or is that it? Is that it? No, don't, is that? No, that's not it. So what's the recursive case? Wait, or is that it?
Or it'd be add XL and then a bracket X.
Oh, and then we see what, yeah, we see if we break the third argument into a head and a tail, first and a rest. So add XL, and then the first matches X. Okay, let's see. Well, anyway, are we good with that? Okay, now the next one, the next little issue that we're going to look at is negation. And this is a very interesting, what we're going to do, our author has really good examples here to illustrate the principles. And this next little problem that he's come up with is a problem of classification into categories. Now, I know we have at least one sportsman here, athlete. Okay, now, so check this out. What do you suppose the predicate is? Beat Tom Jim. That means what happened? Yep. Maybe this is like tennis. I think our author says they're playing tennis. And then beat and Tom. So Tom beats Jim, Ann turns around and beats Tom. And then Pat turns around and beats Jim. Okay? Are we good? So those are our 3 facts, okay, of who beat whom. All right? Now, what we're going to do now is we're going to have categories, right? We're going to characterize people by their win-loss records, seeing as how we're competitive, right? And in sports, that's competition. So here's what we're going to do. What we want is a predicate called class that we're going to make a rule for. And the first class is also a 2-ary, and the arity is 2. And the first is player, and the second is category. And here's what we want to do. We're going to define 3 categories. So who's a winner? Yeah, a winner is one who wins all of his games. Undefeated, numero uno. Yeah? And then, who's the fighter? Who's the fighter? Well, yeah, but I mean, in general, you deduced that Tom was. Of course, we're going to have to program it. We're going to have to define it so that it works that way. But it's somebody who does what? Wins some and loses. And now what's obviously the last category? No, we don't call him loser. We call him what? We call him the sportsman. Because he hangs in there and he keeps playing even though he loses every game. What a good sport. Excellent example. All right, so, I mean, just using these categories and assuming that we have programmed class correctly, what should happen if I do class? And here again, we will assume that for now, for these first few examples, we will assume that the second one is like the output one. So if I say class Tom capital C, what should what should happen? Oh yeah, you said. You said that he should be a fighter. And that's what he is. And what about Ann? What class is Ann in? What class is Ann in? You're right, never lost a game. What about Pat? Another fighter? No, Pat's a winner, right? Because Pat won a game and didn't lose any, right? And what about Jim? Yeah, not a loser, definitely. He's a sportsman, but look, are there more solutions? Well, he's a sportsman twice, right? Why do you suppose he's a sportsman twice? Because he lost twice, yeah. Okay? Now, is everybody cool? So now, what's the logic for doing this classification? So what we need to do is first of all, we need to set up what the rule, let's set up what the rules for the fighter and the winner and the sportsman. So what's going to be the rule for fighter? X is a fighter if there is what? Here, the first part of it, if there's some what? Some y that X beat Y, and obviously some what? Yes, there's some Z such that Z beat X. So that's the rule for a fighter. Are we good? And what's the rule for a winner? Now here's where it gets a little tricky. What's the rule for a winner? X is a winner if what? If there's what? Yeah, X has to beat some Y, but then what else? Now here's where it gets tricky. Yeah, not beaten by anybody. So there can't be a Z that beat X. Now how are we going to do this not thing? Okay, that's kind of what we're... And what's the... Okay, so those are the rules for a fighter. And if a person's not a fighter or a winner, then what is that person? Okay, so here's going to be our logic. If X beat somebody and X was beaten by somebody, what do we know? And then X is a fighter. But now what we're going to do is we're going to use this cut. Otherwise, what do we know? You see what we mean by otherwise? So otherwise, in other words, if that first one didn't happen, well, but there has to be, otherwise if X beats somebody. and the other, are you with me?
And nobody beat X.
Then X is a winner. Otherwise, but now, otherwise, in order to be a loser, you have to be a player. Sorry, in order to be a sportsman, you have to be a player. In order to be a sportsman, you have to be a player. So otherwise, if X got beaten by somebody, then what? Then what? X is a sportsman. Okay, so now, can we? So that's the logic. So now, how can we do this with cuts? So class X fighter if. Come on. If
Beat
beat XY, actually beat X anybody, right? Because Y would be anonymous. Okay, if beat X any, and what?
beat
Beat anybody X, and then what? Cut. So if both of those succeed, then he's a fighter and we know he's not anything else. But if one of them fails, we won't do the cut and we'll go to the next one. Now are we seeing how these red cuts work? Okay, so now what's our next rule?
Class X winner.
Class X winner if, so we have the logic up there. Yes, beat X anybody. And now again, a what? A cut. Okay? So now the only way we can get, so if that fails, if beat X anybody fails, then, yeah, class X sportsman if, but now what does he have to do? I mean, what has to be true? Beat anyone X. Now, does everybody see how that logic worked? Now watch, now I gave you we see that these work whenever this C is, whenever we put a person's name here and we put this second one as a variable. But look, you guys, can you predict this? I want to see if you can predict this. There's the code up there. Now see if you can predict this. Actually, I think we did this one before. Let's just repeat it. Class Gym C. Let's just do this observation here. What did we say happened here? It happened twice, right? Now, can you see why it happened twice? Because it failed here, it failed here, it failed here, didn't make the cut. Yeah, yeah. And here, it succeeded here, and then it backtracked, and then it succeeded again. Okay, so that's why the 2. Yeah? Look.
Yeah.
Oh, that's an interesting, yeah, that would be an interesting experiment for you to do. Okay, yeah, the question was, could you put a cut here and then have that only happen once? And I think you might be right, but we'll see. Okay, now check this out. Here, what would you hope if we said class X winner? So now what are we asking, you guys? Who is a winner? Now hopefully, what should X be? Hopefully it should be Ann. But can you predict what would happen here? Because look, oops. Look, here it is. Beat Tom Jim, beat Ann Tom, beat Pat Jim. Can you tell what's going to happen? Can anybody predict this? Ooh, I went too far. Sorry. Whoa, I thought I was going to... Wait, where am I? Yeah, okay, here's the code. Can you tell what happens here? Oh. Yeah, but was Tom a winner? You are right. Good prediction. What's the problem? Right, he beat someone, but he wasn't a winner because he also lost. Yeah. Mm-hmm. So that's one shortcoming. Here's another one.
Why did it only return 5? What does it say? Shouldn't it have returned
Because the cut is not gonna switch for more.
Yeah. Oh, yeah, you're right. Why, it seemed like it didn't even search for and after that. Right. Good observation. Okay. So that's what happens when we do class X winner. Now, what happens if we do this? Just to verify kind of the same kind of thing, if we do class Tom winner, okay? By the same reasoning, what's this going to be? What's going to happen here? Yeah, it's going to say yes, even though it should be no. And here's another thing. What do you suppose happens if we want suppose we do class and we want to have capital who and capital category? What would be nice? If it gave everyone in their category, but what does it do? It says category is fighter, who equals Tom. Okay, and that's it. Okay, with no backtracking, there's no more solutions. Are you with me? So we set all this up to say this, to explore negation as failure. Now, and here's the thing. We're going to illustrate this by introducing the not predicate. So, and the example we're going to use is, we know cat is an animal, dog is an animal, snake is an animal, and we want the rule, Mary likes all animals but snakes. Okay? So here's going to be, and so here, just to demo this, if we say likes Mary snake, what should happen? And if we say likes Mary cat, what should happen? Yes. So Mary likes all animals but snakes. So here's our logic. If X is a snake, then what? Mary likes snake is not true. Okay? Otherwise, if X is an animal, then Mary likes X. Yeah? That's going to be our logic. But in order to use this, what we need are two interesting atoms. One is called true. Now watch this demo. Now what do you suppose happens if I type true? Do you suppose that will succeed or fail? Yeah, and what happens if I type fail? Obviously what's going to happen? Fail. Okay, so what is our conclusion here? True always succeeds, fail always fails. So those are some tools that we have to work with. So check this out, you guys. How are we going to program Mary likes all animals but snakes using this logic? If X is a snake, then Mary likes X is not true. Such that if I do likes Mary snake, we get no. So how are we going to program this? Oh, and the demo was true always succeeds and fail always fails. So how are we going to program this? Likes what?
Likes
Mary.
snake.
Oh, by the way, I'm not sure if this is still true. There was a typo in the book for this rule. Likes Mary X if, now what? Now what did you say? If X match snake, and then cut, and then fail. Now, does everybody see why that works? Okay.
Did you fail cut?
No. Because if you did fail cut, the cut would never execute. Are you with me? Remember that when you get to the cut, it always succeeds going through the cut. But fail always fails. If you said snake, comma, fail, cut, the cut would never execute. Because fail would fail.
Oh.
It would backtrack from that point, and the cut would never execute.
No, wait, but backtracking only works when you go back, not when you go forward.
I know, but what I'm saying is, if you said, would it work if you said X match snake, comma, fail, comma, cut?
No.
What I'm saying is, in that situation, the cut would never execute because you'd never get past fail.
But you don't need it to execute when you're going
Well, except that the logic, now what's the next rule?
If you didn't have a cut, you didn't.
Wait. Before we do that, let's go to the next rule. So what's the next rule?
Like
Likes, marry.
animal.
Animal is not. Animal is a predicate.
So we put animal parentheses X.
No. Oh, now you're thinking functional.
Like,
Not. You can't.
X if in-
Yes. Yeah. Now that's right. Likes, marry X if what? See, you were trying to put that in the parameter list, right? That's functional. This is declarative. Okay, so what? Yeah, I know, we got all these paradigms all mixed up. Okay, so what? If what? If animal X. Are we good? Oh, this is such good stuff.
If you didn't have the cut on the first one, even if X and snake didn't succeed, would it still fail?
It would still fail, but on the other hand, then it would also succeed with animal, because snake is an animal. Now, did you get that? Do you see that? How that? Are we good?
So putting that in Mary likes Mary X will give you all animals she likes?
Actually, that's a good question.
Well, I was saying if X is
What-
not snake and you didn't have the cut, would it still fail?
Wait, now you got a lot of ifs there. Say that again. What's your question?
If X is not snake and you didn't have the cut, would it still fail?
If X is not, well, it would fail because X was not snake. So it wouldn't even do this. It would fail here. So what difference is it? You see? Are you with? Yeah. Yeah? Okay? Okay, so now, and now another way to write this, there's another way to write this. We can write this as one clause, and there's no difference between these two. If you say likes to, so here's a second version, likes to marry X if X match snake cut fail, and then semicolon, and then animal X. But there's no difference between these two. All right? So if we say likes to marry, if we say likes to marry snake, that's still no. And if we say likes to marry cat, it still says yes. Okay, so there's no difference. But now here's my question. Here's another prediction. What about likes marry what? And this, someone asked this a second ago. Likes marry capital what? Now, what do you suppose happens here? Do you think that's what you would hope, but let's analyze it. What's going to happen? No. And it doesn't matter which version you use because they're equivalent. Look. Now, why the heck is that happening? Yeah. Yeah. Because what is a variable, then it matches snake. So what is instantiated to snake, and then it fails. But once it fails, it went through the cut, it couldn't go back. Okay?
Do we need the cut for this?
Hmm?
Do we need the cut for this? Like if we get rid of the cut, will it work for that?
No, because the cut is a red cut. You know, we did these rules with red cuts. So now what we need is not.
Wait, why doesn't it just go to the next one? The second one.
No. Well, okay, well, shoot. Here's the problem. We're all out of time. So you know what we're going to have to do? I think what we're going to have to do is, I was hoping we could get all the way through the end of this, but we're right at the apex of our discussion, and we're out of time. So I think what we're going to have to do is have the homework due Thursday and finish this up. Well, I'll have to see, we'll have to regroup and see what to do with the last homework assignment.